Hello, everybody. Good morning.
Good morning.
Good morning.
Good morning.
Moti.
You are welcome, Professor IVER LAUERMANN, Professor YAHYA TAYALATI. I just
Thank you,
reached
Professor
the complete of the invitation.
Okay, excellent. Okay, so we should start, Moti.
Yeah.
Good morning, everybody. Thank you for coming. I'm Tayalati Yahya from the University Mohammed V in Rabat. First of all, and on behalf of the organizing committee, I would like to thank Professor IVER LAUERMANN, who accepted this invitation to this fourth international conference on materials and environmental science.
Hello, can you hear me?
There's some problem with the sounds from the chairman.
Yeah.
Maybe if it's persists, maybe just Professor Hamoudi can introduce you and go ahead. Yeah.
Yeah, I don't hear the chairman anymore.
Research.
Hamoudi? We don't hear you.
Professor Tayalati, we don't hear you.
And
problem with the microphone.
Dr. IVER LAUERMANN?
Yes, I'm here.
I think it's better if you start your talk.
Okay, I will. So you can understand me, you can hear me?
Yes.
Yes,
okay.
Sure.
Okay.
Yes.
Okay.
Yes.
Very good. So I will just start. Yeah. So first of all, let me thank the organizers for inviting me to this conference. And I would also like to thank my former colleague and good friend Ahmed Inawi, who invited me. And I will talk about tandem solar cells, a fairly recent development. We heard about tandem solar cells yesterday in the talk from Thomas Hanappel. This was a very efficient system that he showed, but like he said, quite expensive. And we are now going to hear about cheaper systems, thin film systems, and these will be monolithic perovskite CIGS tandem solar cells. And I'll focus especially on the interface and material optimization of the recombination junction. And I would like to thank my co-authors, Tobias Bertram, Ivona Kafetiska, Christian Kaufmann, Natalia Maticic, Rutger Schladmann, and Robert Wenisch. Okay, and when you work in this field of tandem cells, normally you need to collaborate with others because the top cell and the bottom cell are made with very different technologies. So not one group can make normally a complete tandem solar cell. So here we collaborate with the young investigator group of Steve Albrecht at the HZB, especially with his PhD student Amran Alashuri and his former postdoc Marco Joost. We collaborate with the University of Eindhoven, Maria Adriana Creatore, And the bottom cells are made again at HZB, the Helmholtz Center Berlin, at the Institute PVCOMB, by the CIGS group, which is led by Christian Kaufmann, and Tobias Bertram and Jakob Lauche have been instrumental in making these bottom cells. So what's the outline? I will quickly introduce the Helmholtz Zentrum Berlin. I will talk about why we go for tandem solar cells, and then jump into the topic of perovskite CIGS tandems. And in the end, I will talk about the recent developments at HZB. So the Helmholtz Zentrum Berlin is a national research institution. It is part of the Helmholtz Society, and it was formed by merging the former Hahn-Meitner Institute in Berlin, the HMI, which has a tradition back to the 50s, and the Berlin Electron Storage Ring BESI 2, which is a synchrotron facility. So the institute provides synchrotron radiation to a wide community, to a worldwide community. And people from all over the world come here normally in normal times for their experiments at the synchrotron. But we also run an ion source, which is now used for medical purposes. And we have our own in-house research, especially in the field of energy, energy materials, storage, information technology, and specifically thin film photovoltaics. Excuse me, and that's what I will talk about. Myself, I work in the division of renewable energy in the Institute PVCOMB, the Competence Center for Photovoltaics. And we develop photovoltaic cells, especially thin film solar cells and very advanced silicon solar cells, heterojunction solar cells. Okay, so all of you know this. If we look at the solar spectrum, we have a certain distribution of the power density to different wavelengths or energies. And if we look at common solar cell materials, that is, if we look at, let me just get the laser pointer here. If we look at different materials that are currently used for solar cells, and we look at the absorption edge, we can see that we can never cover the whole spectrum. And especially, we cannot get the whole power density from the solar spectrum with a individual material like silicon, for example. Now, why is that? Well, in order to absorb the light, we need to overcome the band gap in our semiconductor material. We've got the valence band, the conduction band, and the band gap in between. And if the light doesn't have enough energy to excite charge carriers from the valence to the conduction band, it is not doesn't get absorbed. It's transparent. So that part of the light is lost. If we have just the right energy for this transition, we can utilize a very large portion of that light. If we have higher energy, we can only utilize the part that corresponds to the band gap, because carriers that get excited to a higher level very quickly lose their energy and end up here at the band gap. So the result is, if we look at this graph here, we have, depending on the band gap of the material, a certain portion of usable electric power. And you can see this is on the order of 30%. And we lose the high energy electrons by relaxation to the band edges, and we cannot even use the below band gap photons. So these are the losses if we use just a single material. Now, if we look at single materials today and we look at this efficiency curve, which is basically the Shockley-Queisser equation of the theoretical limit for single junction solar cells, And we look at the thin film material CIGS. I'll come to that in a moment. We are here in the range of 23%, today a little higher even, and this is for small laboratory samples. And if we look at this new material, which I'll also come to in a moment, perovskite, we are also in the same range. And these have different band gaps. And now we can combine these and look what we get. If we look at the CIGS, which here we call the bottom cell because it has the lower band gap, the blue curve shows us the utilization of the solar power by a single material. And the green curve here shows us the utilization by the higher band gap perovskite material. So it starts at a higher energy at a lower wavelength. And now, if we combine these two, the blue part and this green part, we get the utilization in a tandem. So this is higher than just the blue part alone or just the green part alone. We still have some thermalization losses. In order to improve that further, we would need more materials. We can combine 3, 4, 5, infinite number of different materials, and then we would get more and more from the solar spectrum. But of course, it makes it much more difficult, and we are going for cheap solutions and for simple, for easy to make tandems. Now, if we look at a tandem, there are several ways of combining materials. We can, for example, in a so-called 4-terminal device, simply stack them, mechanically stack 2 solar cells. The upper one with the larger band gap is partially transparent for the red light, for the long wavelength. And so it absorbs the high energy light, and the red light goes to the bottom cell, and both of them are individually connected to an MPP tracker, and we can utilize the power. Now, because here we have 4 terminals, this is called a 4-terminal or 4T tandem. However, we have extra encapsulation here. We have extra electrodes. We have the cables, the wiring and everything. So this makes it more technologically difficult and more difficult to produce these. It would be easier if we had a 2-terminal device, which means all the layers are stacked on top of each other. And so this is what we're going for. We want to combine a bottom cell, a thin film bottom cell of CIGS, copper, indium, gallium diselenide, with a large band gap perovskite. Now, the advantage of having a 2-terminal is we don't need all these cables. We can make the cells in one go, so to say, in any kind of fabrication site where they have the glass substrates basically entering the machine on one side, and all the thin layers are deposited. At the end, we have the ready device. But we need to adopt the absorber thickness so that both cells provide the same current, because there are 2 electrical devices basically put in series. So the current is limited by the smaller current. So we have to make sure that these currents are matched. We also need what we call a recombination junction between these 2 cells, and I will come to that in a moment. And what is important, when we deposit the top cell onto the bottom cell, we cannot use high temperatures because otherwise we'll destroy the bottom cell. And that's why these perovskites are so advantageous. In a 4-terminal tandem, we do not require this current matching because we have 2 independent devices. And so we can combine many different band gaps, thicknesses, and so on. But we need 3 transparent, highly conductive contacts because we need those terminals. So if we look at the efficiency, and here we are comparing the 4-terminal device to the 2-terminal device. We're looking at the band gap of the bottom cell and the band gap of the top cell. And the color scheme gives us the efficiency. So in the yellow part, we go to 45% efficiency, which is very good for a solar cell. We can see here in the 4-terminal tandem, we end up at a combination of 0.94 EV for the bottom cell and 1.7 for the top cell. And it's not too different for the 2-terminal device, but here you can see the sweet spot. This yellow area is much smaller. So you are constrained to a certain combination of top and bottom band gaps. And if we now talk about the two individual technologies that we're utilizing, as a bottom cell, low band gap, we use the well-known copper indium gallium diselenide, which is a commercial product already. It's a thin film device. And for the top cell, we're using these fairly recent methyl ammonium lead iodide based or perovskite solar cells. Now, the actual absorber, which initially was methyl ammonium lead iodized, can be modified in this stack. We can replace the cations and the anions, and that way we can change the band gap and choose the optimum material for a tandem solar cell. So we've got the bottom cell, we've got a top cell, and now we aim to combine them to a tandem. Now, as I said, the simple way is a 4-terminal, and this has been shown by ZSW, for example. This is our semi-transparent top cell, the perovskite. It's actually a module. And here we have the bottom cell, the CIGS. This is not what we're doing at HZB. This is another example here where you see all these layers. Again, a bottom cell independent of a top cell with an efficiency of more than 20%. This was shown by EMPA already in 2015. We are going for the 2-terminal device. So we have the substrate, we have the bottom cell, CIGS, we have our transparent conductive material at the top of the bottom cell. And here we have the top cell, the perovskite, with this fairly complicated composition with the right band gap. And now the light passes through the top cell, reaches the bottom cell. Now what's crucial is this interface here between the two cells we call the recombination junction. And this material has to meet certain criteria. Of course, it has to be transparent for the red light, which needs to pass through here. It needs to be electrically conductive. And it needs to have certain other properties. I'll come to that in a moment. The first cell in this scheme was shown in 2015 by Theodor Todorov. And here we have the CIGS bottom cell, the standard cell. Here we have a thin layer of conductive oxide and a hole conducting material. And this is only this thin layer is the perovskite top cell, and then aluminium PCBM, a top contact. And at that time, they had almost 11% efficiency. This cell was shown in 2018. What they did was, in order to avoid the rough surface of the CIGS, you can see how rough it is, because this gives big problems with the thin perovskite layer on top. They actually polished this part here. They made a very small cell, they polished it, and then put on top the top cell. And they reached 22.4%, so a big jump from the previous. So when we look at the energetics of this cell, here we have the energy versus the vacuum energy, energy of the electrons. This is our bottom cell, the CIGS, small band gap. This is the back contact. And now we have to build the stack in a way that the electrons from this cell travel down towards the recombination junction, and the holes in the top cell travel the other way towards the recombination junction. And here they recombine, and thus we have a current flow through the whole cell. So each of these materials here has to be designed in a way that they perfectly match, that we don't lose voltage here in this part of the cell. And now I zoomed into this recombination junction. This material in this specific configuration that we use has to be a p-type material with a certain position of the valence band. It should have a large band gap because the long wavelength light has to pass through. And what we do is we screen known p-conductors. We also have partners that use DFT calculations to provide new materials, the University of Paderborn. And then we synthesize them and we test them, and we do our interface characterization using XPS, photoemission spectroscopy, and using also X-ray absorption spectroscopy at the Bessey synchrotron. And of course, many of you are familiar with the principle of X-ray photoelectron spectroscopy. We irradiate the sample with X-rays. We look at the emitted electrons, and this is the machine that we use, where we can actually prepare samples in this part and then move them over to the analysis where we do XPS. This is a picture of my laboratory with the machine. And what we get is a spectrum like this. For example, if we look at nickel oxide, which is a material that we use, the nickel 2p spectrum. And here we are interested in the ratio between nickel 2 plus and nickel 3 plus. So we have to deconvolute the spectrum to find out what the composition of the sample is. And this is crucial for the p conductivity and for the conductivity and also for the transparency at a whole. We can also use ultraviolet light, then we call it ultraviolet photoelectron spectroscopy. And here we can determine the work function of the material, the valence band position, which is crucial for the setup of the whole cell. We use the synchrotron for X-ray absorption. And there we look at the edge, the absorption edge of a certain material, for example, in this case, nickel oxide. And these are data that we just got last week at a short beam time at the Bessey synchrotron. Here we see the energy and basically the count rate, which gives you the absorption coefficient of the material. And from this fine structure, we can determine the structure, especially the distance between the next neighbors in the material that we're looking at. I cannot go into the details, but this is a very interesting material to see the differences between different, for example, in this case, preparation methods of sputtered nickel oxide. Now we work with nickel oxide, and the first result, first very nice efficiency was achieved just a year ago, or almost 2 years ago, in collaboration with the group of Maria Adriana Creatore in Eindhoven. They provided the nickel oxide, which was used in the recombination junction. This is what it looks like, CIGS, recombination junction, fairly complicated composition, and then on top, the perovskite. And this is when you look at the current matching. This is the part of the current from the solar cell that comes from the perovskite, from the high energy light. This is the part from the bottom cell, the CIGS, and they have to be as close as possible in order to reach current matching. Now, another material that is used for an efficient recombination junction are organic molecules, and they form just a single molecular layer, a self-assembled monolayer, or SAM. So they're very thin, they absorb almost no light, and the electronic properties can be tuned. And this is a collaboration with a group in Lithuania, and they developed this material. It has been patented by now. And so with that, the efficiencies went up. So here we have, again, CIGS, we have the perovskite, and in between we have this SAM, the self-assembled monolayer, and an efficiency of 23.2%. And this is also a recent development. And now they have even reached more than 24% here. These are, this, by the way, many of you know the so-called NREL charts. This chart is updated annually by a research institute in the United States, NREL, and we have all the records, solar cells, different technologies, and these are perovskite CIGS tandem solar cells. And these, by the way, are perovskite silicon solar cells, where HZB also currently holds the record. And again, this was developed in the group of Steve Albrecht. So right now, we have the world record here at HZB for these solar cells. And for these specific solar cells, one has to say, so we've got a thin film, a all thin film tandem device, and it's fairly cheap to make. And the perovskites, I haven't talked about that, just require wet chemical deposition, low temperature process. So these devices can be made without destroying by too much heat the bottom cell. And this is a big advantage over other tandem devices where you need high temperature processes for the top cell. So the outlook, what are we doing in the future? We know these devices work quite well, and we know the recombination junction, it has to say, sorry, here, they work quite well, but we still don't quite understand how they work, and we know there's still room for improvement. So we need to understand and improve the interfaces. We want to look for other materials. There are many Hall conductors that could be used, and we need to find those that are also stable in the long run. We haven't talked about that. We think that it would be good to replace all the organic Hall conductors with inorganic materials for reasons of stability. And as far as the bottom cell goes, we think it would be advantageous to reduce the roughness of this TCO and of the entire bottom cell to make sure that we get a good conformal coverage of the top cell. And we want to reduce the thickness of the TCO because it always has some parasitic absorption of the light, which we want to reduce. And then there's still room to optimize the band gap of the bottom cell absorbers to get closer to that maximum efficiency that I showed you, that is attainable in a two-terminal device. Okay, and with that, I would like to thank my collaborators, to thank more people from the HZB, because, as I said, these tandem solar cells only work in a collaborative effort. You can never do it alone. And I would like to thank Alexander Steigert, who has been an engineer in our group for a long time, helped a lot, and Amran has made some of the best tandem solar cells in the group of Steve Albrecht. YAHYA was a PhD student who worked on the Hall conductors. Marco Joost was in the group of Steve Albrecht, and he made the first world record cells. Mark Heinemann was in the group of Christian Kaufmann, making the first bottom cells. Steve, as I said, is leading the Young Investigators group, and Ivo Zizek helped us with the X-ray absorption measurements on the nickel oxide. And there's plenty more people, both at HZB and at other places, that I haven't mentioned here. And in the end, I would like to thank our current national project. This is a project together with industry, and they have provided some of the funding for this work. And of course, I would like to thank you for your attention.
Thanks, Professor IVER LAUERMANN. I hope you hear me now. I'm so sorry for my this issue with the internet connection.
Yeah.
So thanks a lot. Thanks a lot for this excellent lecture. I wanted just to say in the beginning that you have a brilliant experience in compound semiconductor in film research, but everyone realized that from your talk with all this experience with X-ray based analysis and use of synchrotron radiations. We really learned a lot.
Sorry, you're still interrupted. I don't hear you.
I hope, okay, I will take it again. So now, how it works now?
Yes, now I hear you.
Okay, perfect. Sorry, so sorry for this issue with the connections. Thanks a lot, Professor LAUERMANN, for this excellent presentation. I wanted just to say in the beginning that you have this brilliant experience in compound semiconductor in film research, and also use of X-ray based analysis and use of synchrotron radiation. But anyone know from your presentation all this, we really learned a lot about the new generation of tandem solar cells, monolithically integrated bottom cells with perovskite based top cell. And I was impressed especially by this profound understanding of interfaces and material properties. We will open now a question. I can see many questions in the chat room from Professor Ahmed Nawi. Maybe you can ask them directly by. Please go ahead, Professor Ahmed Nawi.
Yes, thank you. First of all, thank you, IVER LAUERMANN, for this nice talk and very deeply research. I know your lab and we work together, we publish together, and I know exactly how very good you are. I want to ask you now, as I understand, if I look to the status of the tandem solar cell with silicon, with PIN, perovskite top cell, and monolithically integrated to silicon, compared to CIGS Perovskite, where you are in the same level now in terms of efficiency.
Well, yeah, you saw from the presentation, they are actually quite a bit higher. The silicon perovskite tandems are at 29% now.
Yeah, okay.
Yeah, but the band gap of silicon is the same as we have in CIGS. So there's no reason really why we shouldn't also reach that efficiency even above 30.
Right. My question is, do you think this mismatch in terms of efficiency between silicon perovskite and CIGS perovskite is not coming from the problem of dependency of the fill factor on the current mismatch between the subcells?
Well, we're trying to minimize the current mismatch, of course. But it is indeed a problem of the fill factor. And I think the fill factor is mainly determined by the recombination junction. Currently, the fill factor is low because we have shunts in the material. And shunts, which means a low parallel resistance, reducing the fill factor. These shunts are happen easier in thin film devices because the thin films are very sensitive to handling. And so we often see this issue with shunting of the CIGS thin film due to the handling of the top cell. And this doesn't happen in a silicon, I mean, in a solid wafer, doesn't happen that easily. But it's also a problem of conductivity of the various layers. So that would increase the serial resistance, of course, reducing the fill factor. And it has to do with the band match at the recombination junction. We think there's still a lot to be learned how to optimize that that band alignment.
Yeah. Last question is, there are many methods now used to make solar cell with perovskite and of course with CIGS. There is atomic layer deposition, evaporation, sputtering, inject printing. Which method do you think it will be upscaled in the future?
Well, let me start with the method we're using now for the high efficiency cells, and that's mostly spin coating, because the perovskite and all or many of the subseeding layers are made from solutions, wet chemical methods, but spin coating will not be upscaled, obviously. So we have this young researcher group at HZB led by Eva Unger, and they work on methods like screen printing, slot die coating, and in the group of Bernd Stanowski at PVCom, we are now also installing an evaporation tool for perovskites up to a size of 6 inch. So evaporation will be upscaled. This can be done fairly easily, but of course it depends again on vacuum, fairly expensive equipment. And screen printing works well. Efficiencies for single junction devices have been above 16%, but it still needs to be optimized. So yeah, I think screen printing or slot die coating will be methods that will certainly be upscaled. In the end, we'll have to see where we get the highest efficiencies.
Okay, thank you again for your talk and for all these details. Thank you.
Okay, thank you, Ahmed.
Thanks a lot, Professor Ahmed Nawi. I think also Professor Rashid Tuzani wanted to ask a question. Please go ahead, Professor Rashid Tuzani. Rashid.
Thank you so much, Professor Tayalati. Yes. Do you hear me?
No, I didn't hear you. No, sorry, I don't hear you.
Rashid, you are muted. Could you unmute your mic, please?
And now?
Yes. Yes, it's working.
Now?
Yes, it's working. Please go ahead.
Actually, Professor LAUERMANN, I want to thank you about this nice and excellent lecture. We learn a lot. I saw a slide on nitrogen compounds. You have used some heterocycle compounds.
Sorry, I don't hear you anymore. I just heard using heterocycle compounds, and I assume you mean these SAMs?
Yes.
The Hall conductors, yes.
I saw that you are using also some phosphorus compounds. There's nitrogen and phosphorus oxide.
Yes.
You can give us some advantage of mixing both compounds?
Well, can you actually see the slide with the Hall conductors?
Could you show it in screen?
The last slide, Professor LAUERMANN. when you presented the group.
Yeah, I see. Okay, I thought I'm showing
Can you go
this.
back? Can you go back with the slide?
I'm afraid I think we lost Professor IVER LAUERMANN. I can see